We tend to visualize modern deep learning as massive, glowing webs of interconnected nodes, an architecture so complex it seems to defy human comprehension. But if we pause that network and isolate just a single individual node, that complexity dissolves. At this level, a single perceptron operates on the exact same logic as a logistic regression model. The modern pedagogical approach to data science often obscures this. Students are taught to memorize black box API commands from libraries like scikit-learn, writing one line of code to summon a model without analyzing the mathematical engine running underneath. This leads to a dangerous assumption. We start treating activation functions and loss metrics as if they were arbitrary preferences, clever hacks cobbled together by early computer scientists through trial and error. They're not. Every mechanism inside a classification model can be derived directly from strict statistical axioms. The formulas are mathematically inevitable. We are going to build those formulas from scratch. Understanding this algebraic derivation is the precise threshold that separates a mechanic who blindly calls a function from an engineer who can architect entirely new systems. To classify text, we must first digitize it. We start with an n-dimensional feature vector, representing either raw word frequencies or dense semantic traits. We will call this input x. The model assesses this input by applying a weight vector, w. These weights act as voting power, measuring the importance of every single feature in determining the final classification. This diagram shows the simplest and most efficient operation in linear algebra, the linear combination. The model multiplies the weights by the inputs and projects the entire multidimensional space downward onto a single one-dimensional axis. The result of that projection is z, the logit. It represents the total accumulated evidence for a specific class. Because it is a raw sum, the scale of z stretches outward toward negative and positive infinity. We also add a bias term, b. This acts as an anchor. It physically shifts the entire decision boundary left or right, reflecting the default tendency of the data, entirely independent of the input features. Here we hit our first mathematical roadblock. We are trying to predict a discrete class, but our logit is unbounded. An output of positive 4,000 or negative 12 provides raw evidence, but it cannot be used as a probability. Raw mathematical evidence is useless for a decision-making system unless it can be strictly constrained into a conditional probability between 0 and 1. To fix this unbounded logit, we turn to statistics. We make a specific assumption. The log odds of an event occurring are linearly proportional to our input features. Here is the formal equation for that assumption. The natural logarithm of the probability p divided by 1 minus p is equal to our raw score, z. Our goal is to isolate p. First, we eliminate the natural logarithm by raising both sides to the base e. Next, we multiply both sides by the denominator and factor out p to isolate it entirely on the left side of the equation. We perform a final division, and the math resolves into exactly one form, p equals 1 over 1 plus e to the negative z. Look at the strict behavior of this curve. As the raw evidence approaches positive infinity, the probability maps to exactly 1. As it approaches negative infinity, it maps to 0, and a raw score of 0 lands on a 0.5 decision boundary. If a task requires classifying more than 2 categories, this exact same algebraic logic scales up into multiple dimensions, creating the softmax function. The sigmoid curve is the algebraic consequence of the log odds assumption, the inescapable mathematical mechanism for compressing infinite reality into an absolute probability. Generating a probability is only half the architecture. For the model to train itself, it needs a mathematical referee, a way to measure exactly how wrong its prediction is compared to absolute reality, where the true label is always exactly 0 or 1. We establish this referee using maximum likelihood assessment, relying on the Bernoulli distribution to calculate the probability of our exact dataset given the model's weights. Because computers suffer from floating point underflow when multiplying thousands of tiny fractions, we apply a natural logarithm. This transforms multiplication into a simple addition problem. In calculus, optimization algorithms are designed to find the lowest possible value, not the highest, so we multiply the entire log likelihood by -1. This sequence of steps formally creates binary cross-entropy loss. Here, we compare our newly derived loss function on the right against the mean-squared error metric standardly used in linear regression on the left. When paired with the sigmoid function, mean-squared error produces a jagged, non-convex landscape. A model will easily get trapped in high-altitude local minima, but cross-entropy forms a perfect convex bowl. No matter where the model begins its training, it will roll smoothly to the absolute deepest point. Cross-entropy's convex geometry guarantees that the optimization process will arrive at the global minimum. To navigate that convex bowl, the model utilizes gradient descent, calculating the partial derivative, the exact slope of the loss function relative to its current weights. Because the loss depends on the prediction depends on the logit, and the logit depends on the weights, we apply the chain rule of calculus, multiplying the derivatives of each step. The derivative of the loss function contains a denominator of y hat times 1 minus y hat. Crucially, the derivative of the sigmoid function is exactly y hat times 1 minus y hat. Because those two terms are identical, they perfectly cancel each other out. This identity allows the complex fraction to collapse. The result is this surviving formula. Look closely at this. The instruction to update the machine's weights is simply its prediction error, multiplied by the size of the input signal. The consequences of this are perfectly logical. If the model makes a perfect prediction, the error is 0, and the weight remains unchanged. If a specific word does not appear in the text, the input is 0, and the model inherently knows not to penalize that word's weight. The calculus of machine learning results in a direct feedback loop between prediction error and weight adjustment. The mathematical engine is sound, but real-world data introduces severe structural imbalances. Consider a spam filter, where only 10 out of 10,000 emails are actually malicious. A model could simply guess that every single email is valid. It would achieve a 99.9% accuracy rate while entirely failing its objective. Overall accuracy is a statistical trap. The antidote is this 2x2 grid, the confusion matrix. It separates predictions from reality, forcing us to account for specific failures. Precision isolates the predictions your model claimed were positive and asks what percentage were actually correct. It punishes false positives, situations where the model confidently identifies a threat that isn't there. Recall isolates the actual existing targets in your dataset and asks what percentage your model successfully captured. It punishes false negatives, situations where the model is too blind to see the target at all. You cannot simply calculate the arithmetic average of precision and recall. Averaging masks extreme failures. A model with perfect recall but near zero precision would still average out to a seemingly acceptable 50% score. We require the harmonic mean, known as the F1 score. Because it multiplies the two metrics in the numerator, it acts as a strict mathematical punisher. If either precision or recall drops to a fraction, the overall score immediately plunges to near zero, regardless of how perfect the other metric is. The harmonic mean allows no hiding places for imbalanced predictions. It forces the architecture to balance aggressive detection with rigid caution. The final structural threat to the model is overfitting. If an extremely rare word happens to appear exclusively in positive texts during training, the model will try to force its prediction to an absolute certainty by pushing the weight for that word toward positive infinity. It memorizes the noise. To restrain this, we introduce regularization, a mathematical penalty added directly to the loss function. These two graphs demonstrate how L2 and L1 regularization geometrically constrain the model. L2, or ridge regularization, penalizes the square of the weights. The parabola pulls all the weights downward uniformly, keeping the model calm, but it rarely forces any weight exactly to zero. All features are retained. L1, or lasso regularization, uses the absolute value. This geometry creates a constant sharp gradient right at the origin. It bleeds the weight out of irrelevant features, snapping them exactly to zero. It automatically deletes useless words from the system. When this fully constrained model is deployed to production, these equations are not run sequentially. The input vectors and weights are stacked into massive matrices. Through matrix vectorization, the entire mathematical pipeline we just derived is executed millions of times per second in parallel across GPU hardware. Deep learning operates as a towering architecture of geometric and statistical proofs, where every layer builds upon these same deducible truths.